My name is Shivank Garg. I am Linux kernel developer at AMD. So today I'll be giving an overview of Linux page migration and how did we accelerate it with multi-threading and DMA offloading. So first we'll cover a little bit of background on page migration, why it's important and how it's performed. Then limitations of current implementations, and our proposed enhancements, then some results and future works. Yeah, so let's take a brief introduction on NUMA systems. So on NUMA systems, non-uniform memory access, we have fast local access to memory on its local node and slower remote access on memory on different node. And in these modern memory systems, it's becoming much more complex with evolving hierarchies like CXL, HBM, and GPU nodes, etc. So let's see what is page migration. So page migration refers to physical movement of memory pages to different region or node while a process is active. And virtual address used by process remain unchanged. So let's say this is the process. So currently it's mapped to node 0. So if we migrate from node 0 to node 1, see its virtual address remains same, and now it is mapped to node 1, and it all happens transparently such that process remains active. So this is the kernel's magic trick. So why it's needed? So page migration is an important subsystem in kernel, and it supports other features like NUMA balancing, memory tiering, page promotion, demotion, then compaction, hardware maintenance, and user-driven migrations. Let's see each one of them. So in NUMA balancing, we move memory closer to the task accessing it. For example, this socket, the task is scheduled on socket 1, but memory is on node 0. So each access is remote and slow. So using page migration, we move it to node 1, and now it's local, so it's fast. Then memory tiering. So we have fast memory, for example, DRAM connected to a socket, and then a slow memory, example, CXL, where we can attach cheaper memory. So it may happen that our pages are there on high capacity, slower memory. So we may want to promote it to fast memory for efficient uses. So now after page migration, the memory is promoted to fast memory, and the user application will run much faster after that. Then page migration also help us address fragmentation issues in the system to make space for higher order allocations. For example, in this, the physical node is very fragmented, and there is no room for large pages. So our memory compaction daemon will compact the system, compact the physical pages to one location, so that we have some contiguous chunk of memory where we can allocate higher order allocations. For example, 2 MB pages, THP. Then it also helps us address any possibility of memory failure. So when there is it is suspected that memory can fail, there could be some memory failure, but the page is not corrupted yet. So we would migrate the pages to a different location, and then we can soft offline those suspected regions where there is chance of failure. And so similarly for hot unplug. Then user-driven migrations. So it allows user tools or workloads to control memory placement for users from user space to optimize memory placement in NUMA system. So a user can use system calls like move pages, migrate pages, and mbind to convey such information. Now we saw like what and why. Let's see how. So first we start with a list of folios. Then this list of folios is isolated. Uh, it means like remove the folios from LRU list and then add them to migration list. So we perform those, then we process the list in batches of up to nr max batch migration. So this whole page migration is a multi-phase process, and it happens in batches. So now we have a batch of some folios. First, we unmap the page. We go into unmap stage. So in unmap stage, we allocate a destination folio on target node where we want to allocate, where we want to migrate the page. Then we replace source folio page table entries with the migration page table entries. So migration page table entries is like it's kind of a swap entries where it will tell the user, like if a user falls on the page, it will tell the user to wait. Then we do a single efficient TLB flush. So this happens for all the unmapped folios. Then we come to third stage where it is, then we move in the move stage where we migrate mappings and flags, and then copy content, and then update metadata, LRU list, ref counts, and restore working PTEs. So this all happens in the move stage. It all happens in serially, one by one. So this is the bottleneck we are trying to solve. And then cleanup, where we address any error handling or any page that was not migrated. So we fix that. So now, till now we saw what is page migration, why it's so critical in our performance. Now see the problem and our proposed solution. So in memory migration, we have the memory migration subsystem is very critical because it directly affects the application performance, and we have high page migration cost incurred in large-scale tiered memory systems where frequent page promotion demotion can occur, or CPU-GPU coherent system where GPU memory is exposed as NUMA nodes. So we try to profile the move pages system call to understand the overheads of folio copy. So we saw that in 4 KB folios, 22% of folios, 22% time was taken in folio copy, while 78% time was taken in other operation. And for 2 MB folios, this was 97% of overheads were folio copy overheads, and 3% overheads from other operation. So this shows that there is some, we can optimize this folio copy part to improve the performance of page migration. So modern systems are equipped with powerful hardware accelerator and high CPU core counts. And in current memory migration implementation, we use single-threaded CPU copy. So it underutilizes memory bandwidth, and our ideal CPU cores are not utilized, and hardware acceleration potential remains untapped. So we observe that migration system is moving toward batching. So first we batched migration operation, migrate pages system call to take some number of folios to do the operation. Then we batched TLB flush operation. So instead of doing TLB flush after every page migration, we do it in batch because TLB flush is costly. Then the logical next step is to batch folio content copying. So, so this takes us to the batching folio copy operation. So in current design, for each folio, first we copy folio metadata like flags and mappings, and then copy folio content from source to destination, and then update page table entry with new mappings. So this all is done one by one serially. And this is the main reason why memory bandwidth is underutilized and modern hardware, and we can't take any benefit of modern hardware. So in our proposed design, we decouple the folio copy operation into a separate part. So now we first do in batch copy all the folio metadata and flags and mappings. Then we copy the folio content in batch, and then the rest of the part like updating page table entry with the new mappings. So this batched copy makes it easier for parallelization and hardware offloading. So now we have batched the folios. So this takes us to like how we can make it more efficient. So we use multi-threaded copying with CPU. So in this, we divide the folios. For example, we have now 512 folios. So we divide it into chunks and then distribute it across multiple CPU threads. And then we use work queues to copy data to the target node. And so large folios get more copy throughput boost because of the design because we have less metadata and kernel overheads. But with this approach, this is the open question, like how we can do resource accounting and ensure fairness. Like who will bear the cost of page migration? Now we take one step further to offload the folio copy part to DMA hardware. So in this, we dynamically allocate DMA channels, and then like like normal DMA operation, we map the source and destination folios, prepare DMA descriptor with completion callback, and then submit the transfers across channel in round-robin fashions. For example, we can allocate 8 or 16 channels, and then distribute our folios on those channels, and then issue pending requests, and then wait for completion callback. So this helps us parallelize our folio copy and offload it to hardware. And if there is a error from DMA, if hardware returns error, we will fall back to CPU to ensure successful copying. So, but DMA comes with its own challenges, like DMA is high setup cost. So we need to balance, we need to find a sweet spot where DMA setup costs are less than the benefit it gives. So with this approach, we benchmarked move pages. We did a micro benchmark and checked the results for 4 KB folios. So 4 KB folios didn't show much improvement because of high kernel meta overheads, because there are like, so in multi-threaded CPU case, it's like even with multiple threads copying the data, we didn't see much improvement. And for DMA offloading, performance degraded. This is because there are like high setup overheads, and then we benchmark 2 MB pages. So for 2 MB pages, we see a good performance improvement. For example, so here with 8 threads, we got up to like 3.5x times throughput improvement using CPUs. And this is the baseline. Baseline is native single thread CPU copying on the generic kernel. So, and with DMA offloading, we got a 5.16 times throughput improvement. So 2 MB pages, we saw a good benefit with 2 MB pages because there are less overheads to manage this metadata. For example, there are 512 times less page table entries, and then less effort to manage the list and all. So then there are open questions. So this is still in RFC. So then we have some open questions about performance, like when this we will like solve with more experiments and discussion with community, like when we will select DMA and CPU, and how do we schedule folio copy worker threads across different platforms. For example, in some platforms, for example, in AMD EPYC, we have CCD and CCX. So we need to like efficiently schedule across those. And then do we need non-temporal instruction for CPU-based mem copies? And how do we upscale or downscale worker threads depending on various factors like system uses and all? Then we have to standardize offload copy APIs. And we have to think about how to amortize DMA cost. And then think of resource accounting, like who will bear the migration cost and is it fair? And in future, we plan to test DMA offloading on SDXI. So SDXI is a new age smart data stream accelerator. So it's much more powerful and it has many features. One of them is data offloading. So we think like we will get more benefits with SDXI. And then address open questions and work toward upstreaming. So here are links and references to the patch set where you can look into the code. I didn't go into a lot of details because of limited time, but here you can explore more and you can ping me if there is any feedback. Thank you. So any questions from audience? Yeah. You're talking about this slide? Okay. Yeah, slow memory. So like, so when we attach memory, so this slower memory, it's attached to PCI socket. So, and there like it show as CPU-less NUMA node and it's called CXL node, Compute Express Link node. So that's like recent development in hardware. Yeah, it shows up as a NUMA node, and we can use tools like NUMA CTL to get the distance of those NUMA nodes.
I had a question about over here. I had a question about the multi-threaded copies.
Yeah.
I'm assuming your page migration happens from one NUMA node to another NUMA node, right? So my idea of how pages move between NUMA nodes is through a PCIe Express bus. So how exactly does multi-threading help there?
So we need, I didn't get your question, I think.
My understanding of how pages move from one NUMA node to another is that there's a PCI Express bus where when the kernel requests that this page...
No, it's through like, so different NUMA nodes are connected through this NUMA interconnect. For example, in this diagram, we can see, so if we have to move the data, so we can just copy data from this node to that node using some, like we can use simple mem copy, and then CPU will do the copy from one node to another. So it's going through NUMA interconnect.
Let's just say CPU 0 is connected to node 0.
Yeah.
CPU 15 is connected to node 1.
Yeah.
So if a page should be moved from node 0 to node 1, my understanding is there's a PCI Express bus between the memories itself, which does that.
No, it's not PCI Express bus. So if we use CPU, CPU will do it. And if the memory is on CXL node, then it will go through PCI, but then still CPU is doing it. If we use hardware offloading, like DMA, we will have to set up the DMA, do all those DMA mappings. Then DMA hardware will do it. So I didn't get what you mean by PCI is doing it.
Okay, so node 0 loads the page into the CPU 0. CPU 0 communicates it with CPU 15.
Okay.
And CPU 15 pushes it into node 1. Is that the process?
No, a single CPU will do the task. It will not. Sorry, I didn't get your question. We can connect
Okay, sure,
afterwards.
sure. Also, one more thing about, can you go to the unmap slide?
Okay.
So first you unmap the page, right? So if there's a request, if someone tries to access the page after it's unmapped, how would you handle that kind of situation?
Yeah, so first we lock the page, and then to ensure that there is no further access, we replace the source folio page table entries with the migration page table entries. So it's handled like similar to if a page is swept into swap nodes. So it will like OS will ask the OS will if a user process is requesting for that page which is under migration, it will make it wait. So and it all happens transparently. So the user or process will not know about it.
Hello. Yeah, you also spoke about CXL being one of the connector for your case, right?
Yeah.
Did you also explore on having an accelerator on the CXL side and using that accelerator to do your page migrations?
So you are asking about if I did any experiment with CXL node?
Correct. So in your diagram, you did mention about
Yeah.
being connected to CXL, and CXL is treated as a slow memory.
Yeah, you are talking about this, right?
Yeah, correct.
Yeah.
So you can also have an accelerator on the CXL side, which will very well help you in doing your page migration from CXL node to your fast memory node or vice versa, right?
Yeah.
Instead of your CPM doing it, you can offload the same to the accelerator on the CXL side.
You're saying if I used a hardware accelerator for this?
Yes, exactly.
Yeah, so actually I didn't did any experiment with CXL because there were some setup issues on my system with CXL. So I did normal experiments with DRAM nodes. Yeah, so it's in my plan to do some experiment with CXL, and I believe it will show more benefits because transferring data from CXL is little slow. So hardware accelerator will help on it. Yeah.
Thank you.
What's a TLB and what's its purpose?
TLB.
Yeah.
Yeah, so TLB is translation locus site buffer, and then it's like a cache where you can uh, store like virtual address to physical address mappings. So it's like you don't have to do this whole page table walk. Like I'm saying a lot of OS terms. So this page table walk is very like costly operation, and if we use this TLB, we get to know this physical address very fast. Yeah, so.
Okay. Thank you.
So, and we do, like I mentioned about TLB flushing. So this TLB has some entries about virtual address to physical address mappings. So if we, like now, since we are migrating page, we are moving its location from one physical region to different physical region. So these TLB need to be flushed. Otherwise, it will point us to a wrong location. So to get a consistent view, we do a TLB flush here. So, and one point I missed. So I talked, like I interchangeably used folios and pages in my presentation. So folios is a newer concept in Linux MM. So it's just a contiguous chunk of memory, and it's handled. It is handled as a single unit. So it has some less overheads. Yeah.
Hello. So first, I'll do some shameless advertisement for my talk. If you want to know what is a TLB, you can attend my talk. It is at 1 o'clock. Linux is leap beyond fixed pages. So my question is, hi Shivank, I'm Dev. We have interacted on the list, right? So I was looking at version 2. I think RFC is at version 2, right?
Yeah, correct.
So there weren't any comments. Are you receiving any pushback, or what is the status?
So yeah, I'm working on those comments. So like, what's your question? Like,
In V2, I saw there weren't any comments. I think you posted it some weeks back.
yeah, I posted it in around March before like registration of OSS.
Yeah.
Yeah, and yeah, so it's still in. So we got some comments from community folks in LSFMM.
All right.
Yeah, so I'm working in them. And then ZN from NVIDIA is also looking into it from different use case.
Okay. Okay. Thank you.
You spoke about the challenge with respect to accounting. Can you brief what's the challenge there? Like, is it about which tasks you want to account to, or is it what's the challenge there?
Yeah, so like now we are using kernel threads to move the data. So it's like now like the migration cost will accounted on kernel part. So there's a challenge like how to ensure fairness. For example, like there could be different cases where like memory is migrated and kernel is bearing the cost. So this could be unfair to other processes. So this is.
Yeah, in another case, let's say even if you don't do that, still kernel has to do that job, right? It's still part of the
Yeah.
kernel accounting, should be, no? You may have to do it on behalf of which process. You may be some process, let's say one process is doing this in a continuous manner. Is that the challenge? Like you want to be fair among the process, or?
Yeah, like I have to think about that. On this thing, multi-threading, multi-thread copying with CPU. So ZN is working on that, worked on that. So it's for like a different use case. So I have not looked into it in a detail. Like I worked on this optimization 3 hardware offloading use case. So I have to look into how this fairness challenges come. Like.
Okay, all right.
Hi. To add to the same comment, right? So when the migration happens, take an example that you have a socket which gets allocated by a task. But when the task moves from one group to another C group as such, the memory allocated for the socket would just remain in the initial group as such. That accounting is still like little complex when it comes to migration as such.
So sorry, like there is little echo in this room. So I like it's
So
difficult.
I was just trying to answer here when he asked for accounting about the memory model, right? So what happens is like consider this example. So everything's being in C groups. So a task gets task allocates a socket or a socket connection happens, and the task migrates to another C group as such. So what happens is the initial allocation of stock, the socket memory, right, that stays with the initial group. So what about that kind of, those kinds of issues are still there with, accounting when it comes.
Okay.
So just adding a comment.
Okay, yeah, so you're talking C groups will handle some part, yeah.
No, the accounting goes there. So
Okay.
that's still a problem, when you do a
Yeah.
migration.
Yeah.
Hello. So major bottleneck is coming from the batch copy you said, right? I mean,
Yeah.
other than TLB flush and uh, replacing the mappings. So why is it that you get major throughput improvement with only 2 MB pages? I mean, with large folios? Can you explain more on that?
Yeah,
And moreover, on DMA setup, I didn't get that part. Who is going to be that DMA engine who is going to do the this batch copying operation?
So on the first part, yeah, so why didn't we see any performance benefits with 4 KB pages as compared to 2 MB pages? So 4 KB pages, as compared to 2 MB pages, like we have in 2 MB's PMD entry, we will have 512 4 KB pages, and the overheads to manage those 512 entries, like there will, and then we in those lists, that cost is exceeding our any benefit. So we didn't see any benefit with the 4 KB pages. So because there is a lot of kernel metadata overheads of managing those 512 entries as compared to one large folios. And then with large folio, the other setup cost will be amortized. So it will be distributed over, like it will be divided by 512. So we will see more benefit there.
Okay. So maybe other part that DMA setup you were talking, I didn't get exactly that part. Who exactly is going to do that DMA? I mean, in
Yeah,
sense,
so-
batch copying.
So for that, it will be managed by the kernel. We created this migration offload infrastructure. So we can ask the user can register this offload driver, and then so we can like managing some other subsystem like using sysfs interface. We can do this. We can initialize this offloading driver, and there it will do this stuff.
No. I thought my question was so doing this batching operation, batch copy operation, which is the major time taker. So rather than doing it on CPU, you said that it would be you would do some DMA setup and offload this to hardware. What is that hardware which would do this batch copying?
Okay, what is that hardware? So in every system we have this DMA hardware. So it's used by many other subsystems, and then so I'm targeting on data server chips. So they come with the special hardware. Like for example, in AMD Zen 3, we have this PTDMA hardware. Okay. So that will do that DMA copying, the hardware offloading. And in newer generation, SDXI is coming, so that will manage it.
Okay, and what are the major use cases that would benefit? I understand that hot pages you want to keep with the CPU which is executing and accessing that. But I mean, can you elaborate more on the use cases that would get benefited? And other than data servers, I mean, other use cases, if you have idea like where this will benefit.
Yeah, so so there are use cases. For example, in high performance computing, and now these LLMs are coming. So they have huge memory. So we need to distribute that memory on different NUMA nodes. So it may happen that workload is running on one socket and its memory is on other socket, other remote NUMA node. So we may want to move that memory to the local node. And then CXL, this is also a very new concept in this. And CXL is like we can attach a cheaper memory because memory is very costly. So we have this cheaper memory we can attach to CXL. And earlier there was like some concept of NVMM, non-volatile main memory. So we can attach those cheaper memory to the CXL sockets or PCI bus. So there, like we can have like some cheaper data centers. And then memory failure is also an important use case. So because it may happen that some reason of some particular node is failing. So if our OS suspects that this is going to fail, so we can just migrate our data to different regions so that we don't face any data corruption.
Okay, thank you.
So, for the DMA offloading, you are actually submitting the request and then waiting for the completion callback, right? And that's synchronous. But if you are doing synchronous with DMA, which means that you are not going to reap the full benefits of DMA. And I don't know if it's not possible to do asynchronous DMA with your use case, but it's something you should explore. Otherwise, using DMA wouldn't give you much benefit over CPU copy.
Yeah, I agree with that. I was looking into that, but with asynchronous, like I was facing few challenges, like because we have to return those pages to the memory management again, subsystem. So yeah, if we do asynchronously, then like somewhere we need to have that stuff. So okay, yeah, I agree. I'll look more into it to optimize performance. So as you can see my data, like I'm getting 5 times throughput increase with 16 channels. So it's not that scaling, it's not scaling properly. So we need to do some, we need to put some effort there to improve the scaling, and it will further increase the performance.
And then you also need to do it only for more than 1 megabytes of pages, because if you do it for 4 KB pages, there is an overhead associated with DMA.
Yeah, so we are targeting higher order pages, and so many workloads benefit from higher order pages. So that would be the primary use case for this DMA offloading.
Thank you.
Hi, Shivank. This is Archana. Good talk. I just wanted to learn about if you have explored hardware multi-threading, and I just wanted to know how it fares out in regards to performance in page migration.
What do you mean by hardware multi-threading?
It's a hardware technology, and like multi-threading is enabled on the hardware, so you have like 2 threads running. If anybody can explain it better.
Okay, so it's like simple multi-threading. Like we do software multi-threading, like, okay. And then thread is scheduled on multiple CPU cores. Are you talking about that?
No, so this is different. You can just enable multi-threading, hardware multi-threading, and you can just check your performance with that. And
Okay, sure. I'll look into it. Thank you. There's one question here.
So, hi Shivank, good talk. So how do you explain this decline in performance when you increase number of cores from 8 to 16? As in, is there any explanation?
Yeah, that's an interesting question. So yeah, we did some experiment on that. So in our like this was performed on AMD Zen 3. So we have this, like every socket has this 4 CCDs. So yeah, so when we are scheduling up to 8 threads, so we get this performance benefit. But after 8 threads, we are reusing those CCDs. So our bandwidth is saturating. So that's why we were not seeing any performance benefit after 8 threads. Yeah, so this was this I meant by mentioning platform-specific scheduling, because due to this AMD architecture, we have this CPUs are divided into this different CCD, and each has its own bandwidth limit. So yeah, that's the thing. So the main point is like we need to distribute, or we need to spread those worker threads across different CCDs. So this was the main crux of platform-specific scheduling. So I think we can take any further question in the corridors. Thank you.